If you have tried to build a multi-agent system recently, you have likely hit a severe operational bottleneck. Your context windows max out, and the communication between your agents rapidly degrades into chaos. The standard instinct is to try and control this by writing massive, monolithic system prompts, or by deploying a single master agent to direct all the subagents. In practice, this consistently leads to erratic behavior, looping errors, and stalled workflows. Your execution agents become overwhelmed by the sheer volume of instructions. They start hallucinating tool inputs, or they dump unreadable machine jargon and logs directly into task boards. The architectural root of this problem comes down to a recent industry assumption that the Model Context Protocol, or MCP, should be the universal layer for absolutely all tool interactions. To scale a multi-agent system successfully, you have to abandon the MCP everywhere ideology. What works is a hybrid approach, governed entirely by your central repository. We call this the repo-governed operating layer. It is the optimal architectural standard for agent alignment in 2026. You do not achieve alignment to cross completely different agent runtimes by sending complex API calls between them. You achieve it through shared, plain text markdown files. This diagram maps a standard repository structure, relying on 3 pillars: central governance, task-dependent interfaces, and thin adapters. We will build out this empty structure to demonstrate how treating the repository as the ultimate source of truth aligns AI systems without overloading context windows. We start by populating the /core directory. This is the home for all cross-agent behavioral rules, state machines, and operating contracts. One of the most common failures in multi-agent orchestration is human task management boards, like Plain, becoming polluted with agent internal language. This split screen shows the difference between raw logs and actionable context. To solve this, we add a human task language standard.md file to the core directory. This file explicitly bans machine state language. The standard enforces a strict template. Every update must state in plain English what was done, what the agent found, and a single clear next action. Task management dashboards are built for human operators. Raw reasoning, token metrics, and machine logs must remain completely siloed from that operational surface. You cannot simply prompt a highly technical worker agent to sound more human. It will eventually revert to logging. You must enforce the communication standard mechanically. This diagram outlines the evaluation gate. It acts as a hard system barrier that intercepts all task updates before they can reach the human dashboard. If a worker agent submits an update filled with technical jargon that fails the core language evaluation, the update is blocked from posting. Instead, the failed output is automatically routed to a translator agent, a separate model specifically optimized for natural language processing. The translator agent takes the raw machine log and rewrites it into human operational language. Once rewritten, it easily passes the evaluation gate. This pipeline guarantees clean human handoffs. It allows you to run cheap worker agents that focus purely on execution, while a specialized model handles the communication translation. Next, we move to the /tools directory. The most critical file here is the tool interface policy.md. This scale illustrates a major inefficiency called context bloat. If you force every tool interaction through MCP, you have to load comprehensive registries into the prompt. Injecting massive, dense blocks of JSON schema for every single action overloads the context window, drives up token costs by the tens of thousands, and severely degrades the model's ability to reason. The alternative is leveraging a local command line interface, guided by a lightweight manifest file. As you can see, the token weight of specific CLI commands is a fraction of a full schema. Your policy should dictate that CLI execution is used for deterministic, repeatable operations like git, grep, and local file system scripts. The model already understands these commands natively. MCP, conversely, should be strictly reserved for remote integrations, OAuth-heavy tools, and complex cross-agent API contracts where standardized schemas are actually required. The interface choice must be entirely task-dependent. Minimize your token footprint with CLI wherever possible, and keep MCP focused on complex external abstractions. The final directory in our structure is /adapters. This is where the global repository rules are translated so that specific, disparate agents can ingest them. We use thin adapters. These are strict, agent-specific configuration files. They read the /core markdown to understand the rules, never defining the policy themselves. For example, Codex ingests these rules using an Agents.md file alongside its durable TOML configuration, prioritizing CLI-first execution based on the tool policy. Claude Code maps to the identical system, but it relies on hooks and localized skills to enforce deterministic lifecycle points during execution. Contrast those Python and Node-based tools with an executor like ZeroClaw. As a Rust-based binary, it requires a distinctly different structural adapter setup. ZeroClaw uses native TOML configs for its jobs in sandboxes to enforce the runtime policy. It mechanically checks the manifest to determine which CLI commands it can run autonomously and which require human approval. The primary directive of this layer remains constant. The central markdown dictates the global behavior, while the thin adapter handles the granular runtime execution. Reviewing the complete architecture, you can clearly see the strict separation between the core governance, the tools, the skills, and the native adapters. When we trace a workflow, the efficiency becomes obvious. A ZeroClaw worker receives a task and successfully executes a local CLI script based exactly on the tool interface policy. The worker's raw machine log output passes into the eval gate. Because it is unreadable to a human, it is seamlessly rewritten by a Claude translator agent. Finally, the translated, highly readable update is logged cleanly to the plain dashboard for the project manager to review. Multi-agent systems scale when they are driven by high-level repository contracts. They fail when you try to manage them with micromanaged prompts. The rules for your interfaces are clear. Prioritize CLI for execution to save context tokens, and reserve MCP selectively for heavy external integrations. For your workflows, bundle repeated actions into specific skills to ensure repeatability, and use hooks to enforce strict execution steps. Remember that your agent-specific adapters should only ever be used for runtime loading. They are never the source of truth for your global behavior. Audit your current agent deployments. Implement translation evaluation gates immediately to protect your human operators from deciphering machine logs. By decoupling your operating principles into shared central files, you create a robust hybrid architecture. It is a system that natively scales, easily catches its own communication errors, and accurately aligns with your human engineering teams.